Alright, good morning, class. Or at least it's still morning. We got about 2.5 minutes till it's actually noon, but here we are. We're doing some math, of course. And for our students who are absent for today, these are our blanks. Make sure you fill those in. But what we'll talk about today is some review on radicals and some Pythagorean theorem stuff, which of course we've both seen a little bit of, and we really shouldn't have a huge issue with some of this stuff, other than we may have forgotten a couple of these things. So we'll go ahead and start. The perfect square, right, in key point one, perfect square is how we've defined as a number, a whole number multiplying itself or squaring itself, and that creates a perfect square. And then using the properties of radicals, we want to make sure that radicals are always in the simplest possible form. And we only know that is to be true if it follows these three kind of guidelines here. So 1, 2, and 3 guidelines. Okay, so no perfect squares remaining, the radicand does not contain a fraction, and the radicals appear in the denominator of the fraction. Okay, so a lot of that other stuff. Okay, but before we keep going, something I want us to kind of understand here is that we're going to draw ourselves a radical sign. Okay, we're going to draw an X here, draw a Y right here, and then a Z right there. Okay, and then just give us some basic vocabulary stuff, things that I think might be a little bit helpful for some of us. If it's not all that helpful, that's okay, but it's still a good idea and a good thing for us to know. So the X is what we call the radicand. The Y is what we call the index. And the Z is what we call the coefficient. And of course, we have our radical sign or our radical symbol, which is this kind of, it kind of looks like long division, but not quite. A little bit different. So radical sign or symbol, however we want to say it. Those are the same words, essentially. So those are good things to know. In addition to that, I would also put on our notes some of this stuff. Let's colors. Let's go with orange. Because why not? And to start for today's class, I want us to kind of write in a couple things, right? So I want us to write in our perfect squares. So for instance, it'd be like 1. 1 squared is 1. 2 squared is 4. And we'll keep going from there. 4 squared is 16. 5 squared is 25. 6 squared is 36. And we'll go all the way up to 12, actually. So 7 squared, 9. 8 squared, it's 64. 9 squared, it's 81. 10 squared is 100. 11 squared, 121. And 12 squared is 144. Whew. Bit of a lot of stuff. Okay, a lot of things to keep in mind about and whatnot. But this is going to be useful for us whenever we talk about some of these other problems where we're looking for our perfect squares. So we'll just have that to the side. Obviously, you'll have yours separated, and I have mine in one document, but I already know all this stuff, so it'll be okay for me. Then, in the middle here, we have a square root of a 75. And so what we're going to try to do is we're going to try to figure out, is there any perfect squares in there? And obviously, it's already solved it for us. We know that there is a 25 inside of that perfect square. And so what we're doing here is that we're going from the original radical to this not necessarily new radical. And it's not new because we'll realize that 75 is the same thing as 25 times 3. They're equal to each other. So we didn't really change anything other than kind of represent it in a different way. And we keep doing that over and over and over again. If there is multiplication, so right there, there's multiplication inside of a radical. That means we can split apart the radical into 2 pieces. And you can go back into 1 piece eventually. But because we separated it out, we know that the square root of 25 is, well, 5. And we know the square root of 3 doesn't reduce down to anything, so it'll be square root of 3. And that is how we reduce down a radical. It's actually much simpler than we may think. And so for example, one, in this case, right, what I have done with my classes is set up a t-chart like so. And we're going to list out the number or the factors that we can think of for this number. So for instance, 1 and 108. That part's pretty simple. This is an even number, so it is divisible by 2, and that's going to be 54. 3, and I believe 36. But realize of these first 6 values here that we have a perfect square. Okay, 36 is one of our perfect squares. So as soon as you find a perfect square that's not 1, because 1 is pretty useless, once you find a perfect square that's not 1, stop right there, use those 2 factors. So we know that this 108 is equal to 3 times 36 under that radical. Then we can separate them out. So square root 3 times the square root 36. And this is going to equal 6 times the square root of 3. 6 times the square root of 3 because, well, the square root of 36 is 6. 6 times the square root of 3. You want to leave it like so. Okay, you don't want to leave it as the square root 3 times 6. Don't do that. It's confusing. So you gotta make yourself a note. Confusing. Oops. Don't do. Okay, confusing, don't do that. Make sure that the coefficient is in the front. Then we'll do it for the second one. Again, pretty simple actually. Not really a whole lot that's confusing here other than maybe trying to find our perfect squares. Write a t-chart. 242 is what I'm looking for. 1 and 242, of course. 2 and it looks like 121. 121 is one of our perfect squares, so stop. Stop right there, use those factors. So this is going to be equal to 2 times 122, sorry, like so. Separate them out. 2 times 121, both of them under the square root. And I know that 121 reduces down to 11, so it would be 11 times the square root of 2. That's it for example 1. Now go ahead and try extra example 1 on your own. Try 1 and 2. Try them on your own first, then come back. And once you're back here, we can solve this problem out. So we'll make our t-chart again, 63. 1 and 63, of course. It's odd this time, so we're just going to skip 2. We know 3 is going to be correct here because 3 is divisible by 63, or rather 63 is divisible by 3. That is 21. And I notice a lot of our students kind of stop right here and don't really know what else to do. And a lot of us are missing that 7 times 9 equals 63. And 9, of course, is our perfect square. So square root of 7 times 9 equals the square root of 7 times the square root of 9. And that will reduce down to 3 times the square root of 7. Again, really recommend that you all stop the video and try it on your own first. Same thing with example 2, or either extra example 2 or extra example 1, part 2. All right, got to be a little bit more specific here. And just like so, we're going to do the exact same thing. 192. So 1 times 192, of course. 2, and I believe this was 96. 3 and 64. Stop. 64 is my perfect square, so I'll change it. 3 times 1, oops, wow, I'm messing up there. 3 times 64 inside that square root, make sure it's all in that square root, equals the square root of 3 times the square root of 64, like so. Square root of 64 is 8. 8 times the square root of 3, and that's my answer. Again, it is pretty easy, but it could be a little bit confusing. For our third key point here, what we'll notice is that we have 1 square root for a fraction. Then we change to 2 square roots in a fraction. And notice that we have a 4 in the denominator, and we're able to reduce it down. Okay, this is the nice thing about having this radical lesson is that we kind of remember some of these new skills, or rather old skills, that we may not have remembered from beforehand. So this is definitely one of the better skills to know because you can separate out whenever you need to. But in this problem, let's go ahead and solve out some of these examples. For whatever reason, example 2 is not set up the same way as before, but it's okay. It's perfectly fine. But what we'll realize is that the square root of 15, well, that doesn't have any reduction in it, so we're just going to leave it. But we do know the square root of 64. We just saw it. And that's 8. And we're done. That's it. We just reduced it down. Okay. Extra example 2. Here we do have it looking like how we were supposed to have it, but of course it's not solved out for us, not easily at least. So we'll take this, we'll break it from 1 square root and put it into 2 square roots. Square root 23 over the square root of 9. 23 doesn't have a perfect square inside of it, so we'll leave it. But of course, 9 is a perfect square, and it's just 3. Again, very nice, very nice. Here, number 2, you got to be really careful, okay? The negative is on the outside. You want to leave that negative on the outside. So we'll put equals negative in our fraction. Again, we want to take from our 1 square root to 2 square roots. Square root of 17 over the square root of 100. Of course, we'll keep our negative. Our square root 17 doesn't have anything inside of it that's going to reduce for us, so we'll leave it. And then the square root of 100 is, of course, just 10. And that's our answer. We'll find that a lot of these are pretty simple for the most part. Example 4, or rather key point 4. Key point 4 is actually really important, and it's probably the most confusing concept in the entire lesson, only because it's just kind of weird, okay? The example they give here is, well, we know that we have the square root of 2 as our denominator, right? That's what we have right here. But realize that the square root of 2, or really any square root of any number that doesn't reduce down all the way, is literally infinitely long, right? Because, and there's a problem, it says it approximates to 1.414, but the square root of 2 is much longer than just 3 decimal places. There is no fraction, there is no decimal that can represent the square root of 2 accurately. So instead of essentially dividing 3 by infinity, what we're going to do is we're going to change that infinity in quotations, that square root 2, to not be in our denominator. And that's why this next part is so much more important than we think. So we have our original, that's right here. Then we multiply by a magic 1 in quotations, right? They say magic 1 in quotations, but it's kind of weird to just say magic 1, if I'm being honest, just for me. But realize that what we have here is that the square root of 2 divided by the square root of 2, anything divided by itself is just 1. So we are technically multiplying by 1, even though we're multiplying in quotations by a square root of 2 on the top and the bottom. But in doing so, what happens is that they will multiply each other, just like any other multiplication with fractions. So 3 times the square root of 2, they will multiply. Square root of 2 times the square root of 2, they will multiply. And they combine, just like how we said beforehand, where we can break it apart, we can put it back together, we get the square root of 4, and then we end up with 2, because the square root of 4 is 2. But notice we didn't do anything with the 3 and the square root of 2, because the square root of 3 is not inside of a radical. If it was, then we would conjoin them. And we'll actually see an example right here with example 3 here. So example 3 says, we want to reduce this, we want to rationalize our answer. We don't want the square root of 3 under here. So we'll multiply, or rather, let's take that out. We'll multiply the square root of 3 on both the numerator and the denominator. Remember, we're multiplying by 1, essentially. Well, I get the square root of 5 times the square root of 3 over the square root of 3 times the square root of 3. And that's actually really easy for us. Remember, 5 and 3, they're under a radical, they'll mush together. Multiply each other, we get 15. 3 times 3 is 9. The square root of 9 is 3. So make sure that you get that as your answer here. But not only can you reduce down a radical, you can reduce down some whole numbers, some not whole numbers, but necessarily, but reduce down, simplify some actual numbers, coefficients and whatnot. So we're going to multiply here the square root of 10 because we don't want the square root of 10 in our denominator. We'll put that equal to 5 times the square root of 10. Notice this is exactly like the example that was given to us beforehand, where we're not multiplying anything on the inside because we don't have two radicals. But square root of 10 times square root of 10 is just 10. But realize here that 5 and 10 are coefficients, right? They're just regular numbers. So because they're just regular numbers, we can reduce them down. They're not inside a radical, they're not square, they're not adding anything. So we can just reduce it down like so. And 5 over 10 is 1/2. So the square root of 10 is equal, or rather, 5 times the square root of 10 over 10 is equal to the square root of 10 over 2. Okay. Now, go ahead and take some time, try to solve these last two problems here for example 3. And we'll come back. Well, multiply the square root of 5 over the square root of 5. Remember, we want to get that out of here. We don't want it. So we'll put that equal. We know that 1 times the square root of 5, anything times 1 is just itself. And we know that 5 times the square root of 5, or square root of 5 times square root of 5 is just itself. We get 5. And that's our answer. Actually, pretty simple. Here, this last problem here, we want to make sure that we get that negative, or that square root of 3 out of the denominator here. So we'll multiply by our magic 1, which is the square root of 3, over the square root of 3. We get square root of 10 times the square root of 3. Of course, we know the bottom is just going to be 3. But our numerator is going to be equal to the square root of 10 times 3, which 10 times 3 is 30. And we get this as our answer. Okay, so as long as you get these couple things, you should be pretty good. You should be pretty good here. Key point 5 talks about what we call the Pythagorean theorem and triples. And the part that I've already circled here for you is probably the most important part, is that whenever we are dealing with Pythagorean triples, we have certain kinds of triples: 3, 4, 5, 12, 5, 12, 13, 8, 15, 17, and 7, 24, 25. Okay, we have these certain problems because whenever we do the Pythagorean theorem, they actually equal whole numbers rather than a decimal or a radical. So this is really nice for us to know, because if we can recognize that these are Pythagorean triples, we know exactly what that value should be in comparison to trying to figure it out with Pythagorean theorem. And so you should have that blank there, Pythagorean triple. Okay. And in action, what this looks like, if I look at example 4 here, right, I see that I have a 5 and a 12. If I look back at my table, and I notice right here is 5, 12, and 13. 5 and 12 in my problem here are my legs. 13 is my largest side, which means it's my hypotenuse, which means that x must equal to 13. It only makes sense because our table says so, right? And it's already been proven that this works. But let's go ahead and let's just prove it anyway. We'll use Pythagorean theorem. We get 5 squared plus 12 squared equals x squared. We don't know what x is, right? Hint, hint, wink, wink at this time. And so we solve like normally. We get 25 plus 144 equals x squared. Add these two together, we get 169 equals x squared. X equals the square root of 169, which of course is just 13. That's our answer. And it tells us to say whether or not this is a Pythagorean triple. Yes, it is. We are good. Now try example 4 on your own. Okay, and we come back. So in this problem, we have 7 as a leg, x as a leg, and 14 as the hypotenuse. Let's look back at our table. Do we have anything like that? The only 7 that we see is actually right here, and it's not 14 as the hypotenuse, the largest value. So just because we know that that value doesn't exist there, since we know that 7 is, or 14 is not the highest hypotenuse, or the highest length, meaning it's our hypotenuse, we know for sure this is not a Pythagorean triple. We know that for like 99% of the time. But let's go ahead and solve it anyway. We take our leg, 7 squared, plus our other leg, squared. And our other leg is x because, remember, the hypotenuse is always the largest value, but it's also the one opposite from our right angle. So that equals to 14 squared. And we'll just solve. So 49 is x squared equals 96. Subtract 49 on both sides, we get x squared equal to 147. Take the square root of that, and we'll find that the square root of 147 is not a perfect square, or is not a perfect value. It'll be some sort of decimal value. So because that's the case, we know for sure it's not a Pythagorean triple. Okay. In this think, pair, share, what we can do is that we can create this statement right here and put it with a converse. The converse, of course, where we switch the if and then statements. So what this would say is if a squared plus b squared equals c squared, then a triangle is a right triangle. Very good. Very good. Okay. And how is this helpful when working with triangles? We can say can confirm right triangles. And that's exactly what we'll do in this second example. This is our theorem. And look at that. That is exactly what we wrote in the previous turn talk. Or think, pair, share, I think is what it was. Okay, so because we have that, we know for sure that this must be correct. And we're actually at our last 2 examples. So in this example here, example 5, part A, what we have to do first is we need to determine if, or rather which of our 3 sides here is the largest side. And so we say, well, I know 8 is larger than 7, but is 8 larger than the square root of 113? And we think about it. And we think about what is the closest perfect square. The closest perfect square I can think of is probably 121, right? Because that's 11 squared. Well, we're saying that this is almost 11. And I think almost 11 is going to be larger than 8. So we're going to treat this as our C value. We'll call B our 8 value. We'll call 7 our A value. So we'll write this as a Pythagorean theorem. 7 squared plus 8 squared equals the square root of 113. And that entire quantity is squared. The left-hand side shouldn't be too difficult, right? We have 49 plus 64. But then we get to this part and we're thinking like, I have no idea how to reduce this down. And actually you do. You do know how to do this. Just a quick recap as to how exponents work, right? What this exponent is telling us is that it is the square root of 113 times the square root of 113, which we've already seen examples of beforehand earlier this lesson, where a number inside of a radical times that number inside of a radical, whenever they multiply each other, they just cancel the squares out. So we're actually left with 113. Well, 64 plus 49 is 113. And of course, 113 equals 113. So yes, it is a right triangle. That's pretty easy, pretty clear, pretty good for us. I want you to try B on your own. However, let me give you these couple things before you start. I'll go ahead and give you that 4 times the square root of 95 is our C value. It's our hypotenuse. We'll call 36 our A value. We'll call 15 our B value. You want to be careful though. Whenever we do our C squared, which is equal to 4 times the square root of 95, that entire quantity is squared. Our power rules say that we are supposed to distribute this square to both of our terms, the 4 term and the square root of 95 term. So instead of saying 4 times the square root of 95 squared, it's actually going to be 4 squared times the square root of 95 squared. Which of course we've already talked about, but I wanted to give you some time to do that. So after you've done some time with that, we get 16, because that's 4 squared, times 95, right? Because we already have the square root of 95 squared. And we'll go ahead and put all the other information in. So 36 squared, 15 squared, and 16 times 95 is going to give us the value of, let me make sure it's correct in my notes. It's going to give us 1520. 36 squared is 1,296, I believe. And 15 squared is 225. You add those up, we get 1520 equals 1521. So because they are not equal to each other, not a right triangle. So because that's our conclusion, we can say that we are done. And that is the entirety of lesson 8.0 and 8.1. So I hope you had a very fun time watching this video. Of course, if you have any questions, go ahead and ask me at an appropriate time during class or after school or during the passing period or anything like that at lunch. Okay. But that is the end of our lesson. Hope you'll have a good one, and I will talk to y'all later. Peace.